as you go to less and less force. The amount that it moves becomes less and less, or the time that it takes to move the same distance becomes infinite.
So in that unit, it means if the number is high, that means
you either need a long time or a large force to make any motion in that material. So the great example is the pitch clock, where you have a jar full of pitch and it makes one drop every 50 years.
So if the number is higher, that means it's difficult to move.
Yeah.
So
heating things lowers their viscosity, as a general rule.
So then I don't know. Well, there's force in the unit, but it cannot be directly compared with tension.
No, and as I say, it's not a direct comparison, because the surface tension is constantly pulling, and the gravity is constantly pulling on the wafers, depending on the orientation of the wafers. But if you want to do reflow at room temperature, you would wait an infinite amount of time for that polymer to level itself out. But by heating it up, you reduce the viscosity and accelerate the process.
All right. Thank you. Well, you really help a lot with the experience of the SU8 and the fluid.
We chose the right article.
Yeah. And where are we now? Well, we go to figure 4 now. Are you happy with the... Well, they use HSQ here.
Yeah.
Anyway, let's get back to to the main...
to reduce the reflection, apparently. That's an anti-reflection coating on Metasurface 1.
Oh. So there's index matching or anti-reflection coating, all right?
Yeah.
Oh yeah, AL coating. All right. Figure 4. So they should show in figure 4. What should they show?
The results.
The actual performance, right? The actual performance is working, right?
Yeah.
All right. The figure 4A shows the optical setup. Yeah, obviously it should be reflected to the same angle of the instance.
Yep.
So they should use a beam splitter to separate it from the incident beam. And to measure the reflection. All right. Why the focal length of this thing? Why the beam splitter should be located on the focal distance?
I'm not sure. Is that so that you have parallel beams at the beam splitter?
Yeah.
Because that means that, it needs to be parallel beams at the beam splitter so that all of the light coming in is at the same incident angle.
No, pardon? I don't understand. Well, it doesn't matter. It's already parallel. from just here, from to the infinite. That's what parallel means. Because the object is already in the focal plane. So whatever scattered from the object,
it shouldn't matter for the focal length of the.
Yeah, but I don't know why they bothered to put the beam splitter on the focal length here and here again, and here again. Well, this makes sense because it's imaging plane. But yeah. Anyway, that's a detail that maybe there is a good reason to make it improve the performance, I guess.
Yeah, I don't know.
Yeah. All right, so they're collecting the image. Basically, they just need to rotate the sample.
Okay, right. So they're actually projecting through an object.
Yeah.
To create a image which is projected onto the device.
All right, yeah.
And then they're using that to see what's reflected and what's transmitted. And whether it's reflected at the same angle of it. So
I think that's the right way to prove it.
That's actually a really interesting thing, because what I was saying earlier about the light passing through the object, not necessarily coming back out at the same point, I said the light that travelled through this part might be reflected back from here and come out with a different incident angle at this point.
Yeah, it
and
should
reflect
it back. Yeah.
But actually, by doing it with an image, they prove that the light is not only being reflected back with the same angle of incident,
yeah, but the same point. Yeah, so
but the same spatial information.
They can reform the same image,
which is beautiful.
But still, is that the right way to prove it? Because oh yeah, maybe that's the right way. Because just imagine if there's a mirror here, then if the mirror is rotated with a certain angle,
you get no reflection.
Yeah, we'll not get this image.
Well, you get, at any angle, you get a projection of that image. But so long as the angle is less than the opening angle of the objective lens.
Yeah, we will still get some image, right?
You will, so long as the angle is less than the opening angle of the objective lens. But what you would get is a spatial projection of the object. So when it's at normal incidence, you would see the whole object. It's just like in the camera here. At normal incidence, you see the whole object, and then as I tilt my hand, it gets shorter.
Then what if they will? Yeah. Well, I believe they did this work correctly. But what if they just tweak this lens and the camera and they could reform something very similar? Well, just imagine if this mirror is just the silver mirror with 100% reflection.
Yeah, but
if it's tilted a bit, like 10 degrees or 20 degrees.
So if you only tilt it 10 or 20 degrees, you would still see a shortening of the image on both sides and a compression of the spacing between any of the objects in the image.
Well, yeah, that kind of distortion or compression or shortening things. So it could be somehow tricked by the lens here and camera position here, and I don't know, or or not, but still there is chance that
The only way
it can be deformed again one more time.
the only way you could do that is if you're tilting the camera at the same angle that you're tilting the object at.
All right.
In the opposite direction.
Oh, what about the lens?
Tilting the lens wouldn't do that.
If decentered and tilted, and
I don't think tilting the lens would do it. Because you would then be directing the light further away from your camera. But I don't think that that's what they've done. If you have a look, I can already start to see that
this thing,
the image is there.
Yeah.
And you can see already that the spacing between the resolution markers is consistent between the two images, even at the 10-degree shift. And the other thing that you do see is the objects are flipped. Oh no, that's a different structure. That's a different structure to this one.
Mm-hmm.
Yeah, but it's the same as this one. See the 5.
Isn't it just reflected image or?
No, because this is a square here.
It's rotated.
Square here. That's flipped in the horizontal and the vertical.
Yeah.
Yeah.
So yeah. I see.
So
you see this thing is now flipped
and mirrored.
Mirrored again. Yeah. Right. Yeah.
Yeah. It's funny that you said if they only did this at 10 or 20 degrees, and you see the two things that they've chosen is 10 and 20 degrees.
Yeah.
But
20 is not, 10 is okay. 20 is not very beautiful one. It's still okay.
Yeah, I mean, it's not as beautiful, but it's not as clear. But you can still see that the spacing is consistent.
Yeah.
And that the image is not compressed.
Yeah.
So I think they've done a good job.
Well, anyway, I should ask that question. Is this the right way to prove the concept? And yeah, but
So the big question I have is, what is the opening angle of the objective lens?
well, it's 0.3 NA.
So I'm not very good with lenses. I'm not actually an optics guy.
0.3 means if it's 1, that means it will collect all the light of the hemisphere.
So 180 degrees.
Yeah.
So
if it's 0, that's 0.
Right.
It says sine something, sine theta. Yeah, sine theta. Let's just say it's sine theta. So it's 90 degrees. That's 1. So the propagation direction, and if it can collect the 90 degrees from the propagation direction, that's 1.
Okay.
So it's sine theta. So 0.3 is less than half.
Yes.
Well,
it's 1/3. So it means it can collect 60 degrees.
Sine 30 is half, right?
Yes.
So 30 degrees, well,
But it means it can collect a cone. So if 90 degrees is 1,
yeah.
then 1/3 of that is 30 degrees from the normal.
No, it's sine theta. So sine 30 is half, right? Pi over
Yes,
6.
you're right.
Sine
So
30 is half.
It would be.
So it's less than 30 degrees. So is it right? No, sine 30 is half. Half. Yeah, half square root 1 over with square root 2 over 2 is 45.
Yeah.
And square root 3 over 2 is 60.
Yeah.
Yeah. So that's less than 30 degrees. So somewhere between 0 and 30, maybe more than 15. I don't know. Somewhere between around 15 and 20, I guess. For this data, yeah. The same data we used, yeah.
Now they did say that their devices could collect with a half power intensity to an angle of 60 degrees.
Oh yeah, 60. 60 is all right. Then the objective is collecting only 20 degrees or something.
Yeah.
That means if the angle is tilted with 60 degrees,
you should have no reflected light that was reflected in the standard configuration.
very little. Yeah. I don't know how much is divergent to the thing then, but still very. You should collect very little. Yeah.
Yeah.
But more than half, if it's collected there, that means it's collecting more than just conventional mirror. Yeah.
Oh, significantly more.
Yeah, sure. Yeah.
Like orders of magnitude, several orders of magnitude.
A lot more. Yeah, a lot more.
Because in a conventional mirror, you would only collect scattered light that has been
very little, like 0.1% or something.
Yeah.
All right. Where's this one?
Now they can remove the objective lens.
They're testing polarization, right?
Yeah. Seems to be.
So now incident output polarization is cross-polarized. They got this. It's 45. They got this. I don't know why they did it. This polarized, co-polarized. They got this. Why should they do that?
Don't know.
To show the reflection is I don't know. So to show which polarization was reflected?
But it seems that all of the polarizations are reflected.
Basically, the instant polarization is reflected, but with some other polarization included. So there is some polarization change in the reflection.
Yeah.
So these are very similar. So yeah. So basically, most of reflection keeps the same polarization.
Yeah. It's actually interesting in the third diagram there, the P1, with the cross polarization.
Yeah.
It seems to indicate that there's almost no light coming through at polarization 2.
at the center.
Yeah.
Yeah, what's the center? Why circle? What's the center?
Why does it have symmetry?
Yeah.
Probably because the metasurface has symmetry.
Oh.
A circular symmetry.
Right.
Because this is probably an image of the metasurface as a whole object.
Yeah.
So it's a 600 micron circle that's been.
There's no other things here, so
Yeah.
it's the image of the metasurface. Yeah.
But it's quite interesting that the central regions don't transmit in the same way as the quadrants do. Let's see what they say about it.
Yeah. Would you go for the caption?
Yeah.
All right. Yeah.
You want me to read it?
Yeah.
All right. Characterization of the wavefront, and polarization modifications by the retroreflector. So A is an illustration of the measurement setup, which is what we worked out, and measured images of the object on the back side of the gold mirror and the retroreflector as a function of the retroreflector rotation angle. Okay, so in this image then, this is on the back side of the gold detector, which means that the gold is actually not fully reflective. It's transmitting some.
Oh.
Right?
Oh, was it saying that or?
Oh, actually no, sorry. My apologies. They probably spin this around, so they measure this image. They probably spin the sample around, so they're measuring the image, they're projecting the image onto the gold detector, and looking at it here. And then they flip it around and project it onto the metasurface, and that's the measurement here.
So the retroreflector also flips the image vertically and
so the retroreflector
vertically and horizontally.
Yeah, so in a standard mirror, it only flips it horizontally.
Yeah. The retroreflector flips only vertically.
Well, it flips vertically and horizontally.
No, then it should. If it's already flipped on horizontally.
Yeah.
But this and this have a vertical and horizontally flipped relation. That means this is flipped only vertically.
No, because you're not projecting the flipped image onto this. You're only.
No, this is reflected one.
Yeah, this
so
is reflected,
that's already...
and this is also reflected.
Yes.
So.
The relation between
I see
this
what
and
you're saying.
Yeah,
I see what you're saying. The relation between these two
flipped
twice. Yeah.
So if this is already flipped once, then this is flipped once on the other way.
Yeah.
Am I right?
I
don't know
you're right.
I'm saying right, yeah. But why? So the reflection of the retroreflector is flipping the image in a different way?
Well, I mean, it would make sense that the retroreflector is flipping the image in a different way, because the incident angle is being, you're adding the inverse momentum to change the direction that the light is traveling in. So that would make sense that it flips it in a different way, but it's...
So if they... So in this case, they accidentally rotate in this way. But if they rotate it in a different way, it will flip again back to the original image. So
Oh yeah, okay, I see what you mean. So a 180 degree rotation of this object produces this image. It's not actually flipped twice. It's rotated 180 degrees.
Yeah.
Which is equivalent to flipping twice. I'm intrigued as to how this transform actually plays out.
Oh, so they're the same image, right? Just rotated
It's the same. Yeah, it's the same image, either flipped twice or rotated 180 degrees.
Interesting. Did they intentionally put it this way, or they like to show something?
I'm not sure. I mean, I assume that this is just the measured results in the same orientation each time. I don't think that they've deliberately picked a orientation to confuse us.
Right. Yeah.
Let's see what they say about it. Let's keep reading. So, in the backside, reflected gold on the gold mirror, the retroreflector as a function of retroreflector rotation angle, which is on the right. The insets are expanded views of a smaller area on the images.
What about if this backside gold mirror is they shifted the sample translation, shifted to avoid the metasurface area, then they just measure the reflection on somewhere.
Okay. So rather than rotating the substrate all the way around, they could just measure in a section that's probably a much easier way to make the measurement.
That's probably the same reflection. They will have the same reflection characterization.
Yes.
Of the surface. So, yeah.
So
probably the other side would be very rough and not very good to reflect. Yeah.
So that then suggests that it is actually the
same orientation of the. So they are just measuring the.
Yeah, but what that actually means is that the metasurface is actually doing a rotation or flipping.
Flipping.
Or double flipping. Interesting.
So I mean, if they put this thing here, they rotate it in this way, 90 degrees, then this would be different, right?
I don't think it would be. Because I think it has a circular symmetry. So I don't think rotating the metasurface would change the behavior.
Why would have a circular symmetry?
Well, sorry, I should say hexagonal symmetry. So, well, because the ladder structure is a hexagon. It's a hexagonal lattice, and you can see that this is the hexagonal lattice that they're building.
Yeah.
And you can see that this is a repeating structure. So basically, this is a unit. This would be a unit cell here. This whole section. And when you look at the SEM image, you can see that that's a repeating structure. So I think rotating it by 90 degrees. Oh, actually, no, you're right. Rotating that by 90 degrees should mean the rotation that you observe in the image is flipped by 90 degrees, by 180 degrees. Because then these pillars would be oriented at 45 degrees to where they're currently oriented. So the rotation would happen in a different plane. It doesn't have circular symmetry, you're right.
Well, 45 degrees doesn't Right. Well, anyway,
So
yeah.
if you rotate the structure by 90 degrees,
Well, if it has a hexagonal lattice, then it should be 30 or 60, not 45. If you rotate 90 degrees,
yes,
yeah.
you're right. You're right.
Yeah, but what I mean is, well, it has a lattice, hexagonal lattice as a unit cell, but I don't know how they make the graduation or gradient on the surface. So maybe it doesn't have hexagonal symmetry. They just make gradually on one direction to work it best for one rotational direction.
That's actually one of the interesting things that I'm not quite sure I understand from what we've read of the paper so far.
Yeah.
Is the structure spatially varying?
I think so. Yeah.
As well.
Yeah. No, I'm not spatially varying, but spatially. I think they keep the lattice constant as one number, but they change the diameter. But also, I think they change the diameter gradually. Well, they have probably some unit cell of the one set. So to make work, the one part of the metasurface works as something. Then also change. They repeat the thing, but also changing some parameters.
Yeah. So it would seem to me that the metasurface 1 would need to be reasonably consistent in order to perform the Fourier transform at all times.
Yeah.
And then metasurface 2 would need to be spatially variant to enable the angle selective momentum transform.
What I think is they can make this structure circularly symmetric, so that it doesn't matter how they mount on the mount in the optical setup. But practically, it would be more difficult to make it in that way. So it would be easier to make it it works in one direction only. So if you mount it this way and mount it this way, then it will work in that direction.
Right.
So I think that would be easier, but I don't know how they did. Yeah. So
it does seem from that diagram there in B, it seems to suggest that metasurface 1 and metasurface 2 have different architectures.
Yeah, sure. Yeah. And I expect that this is varying in somehow this way, and this is varying somehow in this way. So it only works you tilt the light in this way, but not to.
Yeah.
But I don't know, because if the shape in the photo looks somehow circular, so probably works in both way, or I don't know. Yeah. And then if it works on only one tilting angle,
I might write to them.
Then if experimentally this beam splitter, so well it works only this tilt, or does it still work
in the other direction?
The other tilt, or it related to this beam splitter or something, but shouldn't. I don't know. Yeah.
That shouldn't matter.
I think it shouldn't matter.
If the retroreflector works at both tilts, then the beam splitter won't have any influence over it. All right, let's finish this caption.
All right, yeah.
So we were at the bandpass filter.
All right.
So a bandpass filter, center wavelength of 850 nanometers, full width half max, bandwidth of 10 nanometers, is placed in front of the camera to reduce the chromatic aberration introduced by the retroreflector.
Yeah, why? I was wondering why it's introduced, but yeah, right, yeah. And because basically they're measuring the same wavelengths of the instance, but yeah, they wanted to improve the image quality. Yeah.
I think it's because they're using the 850 nanometer LED is probably not a single emitter.
Yeah, but then if that's not single emitter, the filter should placed on just right after the LED.
But it doesn't matter if you place it just after the LED or just after just before the camera. It's still the same impact.
No, it does, because if the instant light does something here, and that's filtered out, then that does something. So
but we know here, right? When we look at this image, the different colors are refracted at different angles.
Yeah.
Which is why when we look at this image, you see colors showing up in the structure. So what they're saying is to remove this effect from the object image, they've filtered to the wavelength that they've designed the structure for, because it's been designed for 850 nanometers.
Well, what they're saying is chromatic aberration.
Yeah.
So that suggests that the LED is not
a single
100% monochromatic light source.
Yeah.
So they're
making it monochromatic.
So, but why they put it there? I mean, they can put it here.
Yeah, they could have put it here, they could have put it here, they could have put it anywhere. They just chose to put it.
It's like they put it there, so. The silicon somehow works to broaden the light, and so they filter out.
That's a long bow to draw.
Well.
Because I think if that was actually occurring, this paper would be about fantastic metasurfaces which produce different wavelengths of from incident light.
I mean, I would expect if the light goes through such a complicated structure, it will be broadened up a bit. But I don't know.
Like the wavelength of the light would be broadened?
Yeah. But I don't know, it can be easily filtered with one filter, because maybe the broadening is not very significant. Then it couldn't be filtered with some. What's the filter?
It's 10 nanometer bandwidth.
Then it can be filtered, I think. Yeah. So if the filter is, the purpose of the filter is fully to avoid the chromatic aberration, then it should be placed right next to the light source. But if it's filtering something happening in the metasurface.
I mean, from my perspective, I don't think it's relevant.
Well, it's not a big thing to.
I think.
Yeah, it's not degrading the quality of the whole research. Yeah. So, yeah.
Let's keep moving.
Why did anyway, I wouldn't put it if it doesn't.
You know what probably happened?
What?
The professor said,
"Put it there.
Put in a filter."
Yeah.
And a PhD student went in and went, camera slot, bang, filter, done. And then at the end of the experiment, he showed the results. The professor said, "Oh, this is great. Let's write it up." They went through the whole thing, and then 6 months later, the professor said, "Why have you got the filter in this part?" And the PhD student said, "Well, I just stuck it there." And the professor said, "You should have put it at the beginning." And the PhD student said, "Do you want me to spend 3 months taking the measurements again?"
Wow,
and the professor said, "No, don't worry about it." That's probably what happened.
I don't know why. Yeah, but anyway. So if this chromatic aberration is just by retroreflector, means the instant light should have some broadband.
It has to have for it to be chromatic aberration.
Yeah.
There has to be some chromaticity.
Yeah,
to
probably the instant light. So yeah.
I don't think they're trying to hide anything.
All right. Yeah.
Maybe I'm being too generous, but
anyway, I don't like the filter position here. Just
yeah, and that's fine. You can have your preference about it, but the fact that they show us this picture, which clearly indicates the chromatic aberration that you see.
Yeah, well, maybe this was done by the shining the white light and take a picture.
Yeah, it is done by shining white light and taking a picture.
Oh yeah.
But that clearly demonstrates that there's chromatic aberration.
Right, yeah.
So I'm pretty happy that they're saying to make sure that that chromatic aberration has no influence on our measurement.
All right.
We're putting in a filter. I don't care where it goes, but I'm less pedantic about that than you are.
All
And,
right.
you can have your opinion about that. You're right. It would be better to go directly after the object, or even directly before the object.
Before the object is the best. Yeah.
Yeah.
Then it wouldn't degrade any quality of the
Image.
Yeah. Yep. Anyway. Yeah. All right. Where are we? I'm sorry, I stopped too much.
Okay.
Yeah.
So we're still here. We just finished the bandpass filter.
All right. Yeah.
Okay. So number B is an illustration and setup used for characterization of the polarization of the retroreflector and the images recorded by the camera for different orientations of the polarization axis for P2. Areas of the retroreflector where horizontally polarized incident light is deflected with TE and TM polarizations are labeled BS.
A label and yeah.
Are labeled.
Yeah.
BS beam splitter, L lens, PC polarization controller, FC fiber collimator.
Oh, is it
P-
FC? All right.